Hi guys, I'm Akash. I work for Deliveroo. I manage the platform space at Deliveroo. So today I'll be speaking about cost optimization at scale and how do we do that without causing a hit on availability or reliability on the system. So that's what I'll be speaking about today. So when we speak about cost optimization, any yeah, no worries. Good to go. Cool. So yeah, whenever we talk about cost optimization or reducing our cloud cost, the very first thing any enterprise does is they buy cost saving plans, which sort of brings down your AWS spend. But in our case, we are a food delivery company, so we don't have homogeneous traffic throughout the day. And given the nature of our business, we see a lot of spike during lunch and dinner time, which also represents in this graph. This is an AI generated image which demonstrate how our costs look like. So our baseline usage is covered by savings plan, but we do run a lot of on demand during lunch and dinner peaks. And this is where we wanted to save money. So yeah, as I said, our baseline usage is covered, but we still have a lot of on-demand spikes throughout the day, which we wanted to manage. So to save on the spiky usages, we opted for Spot. Spot there's no demand. AWS just gives it off at a very cheaper price with a lot of caveats. So theoretically, it offers up to 90% discounts over on-demand pricing. But yeah, given it's cheap, it comes with a lot of limitations. So for example, any Spot instance, it can be terminated at any given time. So for example, a company demanded 1,000 instances for on-demand. So the moment they get a request for 1,000 on-demand instances, they'll immediately take back all the Spot instances. So that being said, any Spot instance can go off at any given time. And availability of an Spot instance also fluctuates based on demand. So if AWS has a lot of demand, you'll see less Spot instances available. If it's a lot of hardware is free, they give Spot instances. For example, during Black Fridays or any critical sales, you'll see the Spot market is not that great. And another limitation is it gives you 2-minute notice before it starts terminating your instance. So if it wants to take back the capacity, it gives you a 2-minute notice. You can clean up or do whatever you want. And if you don't do any of that in next 2 minutes, it will forcefully terminate your instance. So these are the limitations with Spot instance. So now to adopt Spot, the workloads must be resilient, stateless, and capable of shutting down quickly. Given now we understand what are the limitations, so what we did was we came up with a criteria to select what all workloads can actually run on Spot. So uh, to ensure a workload can actually handle Spot instance, the criteria that we came up with that the instance should be the service or the workload, it should be able to shut down within 2 minutes because that's the max time AWS will give you. Wait a minute. Yeah. Another thing we did was we ensured that any service which is running at least 2 replicas run on Spot. This is another eligibility criteria that we have added. So our thesis behind this was that we never run more than 50% Spot. So that being said, if a service is running more than 2 replicas, one of its replica will always be on demand, and even if Spot goes completely off, there's something running and managing your traffic. Instead of a complete downtime, you have degraded service, but at least it is running. So that's another criteria that we have defined, that any service should be running more than 2 replicas to be eligible to be running on Spot. And another thing that we do is any service which should not have any stateful thing running on it or shouldn't be using any local storage on it. That's another criteria that we have defined. And there's one more criteria which isn't on the slide, but we ensure that none of the Kafka workers run on Spot instances, because if Kafka workers get disrupted, the entire rebalancing thing is pretty expensive. So we ensure that none of the Kafka workers run on Spot instance. So at this point, we know what are the limitations and how we can get around them. So we have built this criteria, and any service that fulfills this criteria, only those services are eligible to run on Spot. This is our eligibility criteria. So by now we know that what exactly is Spot and what all workloads we should run on Spot. Next thing that we wanted to ensure is we wanted a way to predict if a Spot instance is going to be available or not. This is to ensure that we don't end up getting high interruptions. So, wait a minute. Yeah. Sorry, I'm just struggling. Which slide is there? Yeah. So to get this, we came across AWS's Spot Placement Score API. So this is an API that AWS explores. What it does is it takes a configuration and tells you what are the likelihood of getting a spot instance of that configuration. So when I say configuration, it essentially means the number of instances I want to run. So for example, I say I want to run 250 instances, and then I give what kind of instances I want to run. So based on that configuration, AWS will give me back a score between 0 to 10, where 0 means there's less likelihood of getting an instance, and 10 means that you'll get a Spot instance for 250 instances. So what we did was we wrapped this API and made a metric out of it. So we run this API, trigger this, and emit a metric based on our requirements and get a Spot placement score. And based on that, we take all the decision part. But this obviously have some limitations. So when we started using this API and emitting metric, the moment we went live, we saw that the metric isn't coming in after an hour. And what happened is Spot placement score has a constraint that you can only check SPS for limited number of configurations in a day. What that essentially means is, so in our case, the cluster is always scaling up and down. So if I want to check SPS for 250 instances, that's one configuration. And if I want to check SPS for 260 instances, that's another configuration. So as a cluster scales up and down, for SPS, it's a completely different configuration altogether. So that being said, it started throttling us that you can't check SPS for so many configurations. And initially we wanted to check for, SPS for whatever number of instances we are running at that given point in time. But given this constraint, we couldn't do that. So to overcome this limitation, we came up with a strategy that broadened our SPS visibility without hitting these API limits. I'll take help of a diagram to explain this. So what we did was we use ASG's max size as our metric. So basically, let's say my ASG has max size of 1,000 instances. We break it down into multiple chunks, percentile based capacities. So for example, P10 is 100 instance, P20 is 200 instance, and so on till P100. That way now, instead of checking multiple configurations, we are only checking for 10 configurations at a time, and AWS is fine with that. So at any given point, our Lambda is emitting metric, what's the SPS score for running 200 instance, 300 instance, and so on. And now what we do is we check how many instances we are running. So for example, we are running 300 instances. We check what's the closest SPS score for that. So in this scenario, for 300 instances, 310 instances, P30 is the closest one. We check, okay, what's the SPS score for P30? It's 8.5, and accordingly we take the decision if we want to run Spot or not. So when I say threshold, this is something we had to do a lot of hit and try. So there's no one rule that this works for everyone. We started off with a value of 8, but we realized we are rolling back Spot a lot and paging people for no reason. After running Spot for some 6-7 months, we learned that SPS of 6 is good for us. That's the threshold that we use. If SPS goes below 6, we roll back Spot. If it's above 6, it's fine. So this is a value that we have come up with after running Spot for 6-7 months. So at this point, we know what Spot is, what all workloads we should be running on Spot, and how to take the decision if we should be running Spot at this point or not. So now we needed some automation where we can bake all this logic and without any hurdle roll out Spot or roll back Spot or do anything like that. So what we did was we built an automation around this SPS core, and this allows us to basically proactively roll out Spot, or let's say SPS is trending downwards, so we can roll back Spot, and there are some critical periods where we don't want to run Spot. For example, there's any product launch or something of those sorts. So it helps us to roll it back instantly, and whenever the conditions are favorable or the SPS score is good, we can roll out Spot again without any lot of operational overhead. So that's the idea behind coming up with this automation. So I'll walk you through the key components of this automation. So the very first thing that we have is our determiner function. What it does is it takes a service and analyzes where it should be running, whether it should be, so we defined our eligibility criteria. It runs that eligibility criteria against that service and sees if it is compatible to run on Spot or not. And once it's done that, it also checks if it is running on Spot or not. So for example, service A should be running on Spot and it is not running in Spot. So it will emit that service out, that service A, it should be running here. Next component we have is an updater lambda. It is also a AWS lambda. What it does is errors, and when we started looking into those errors, most of those errors were coinciding with spot interruptions, and upon looking into them, we realized all of these 502 errors actually are caused by spot interruption. So let me walk you through a diagram. So what exactly happens whenever there is a spot interruption notice, ECS will mark that node for drain. Let's say this is a node running 3 tasks, and when the node is marked as draining, it will start moving tasks to other healthy nodes, but it will only kill the running task when the new tasks are up and running. So assume there are these 3 tasks running, task A and B. The replacement tasks are not up and running yet, and the 2-minute window is over. So what happens is this instance gets terminated, and as a part of getting terminated, it first kills all of its processes running on that instance, and then the instance is killed. And between container getting killed and instance getting killed, there's a brief period of 4 to 5 seconds where this instance is still attached as a target on the load balancer, and load balancer can still send traffic. So what happens is when this instance gets traffic, the container is dead and it gets back 502. So if you're a small company, it might not matter to you, but at our scale, it was a big problem and we had to fix it. So to fix this, we came up with another Lambda, and what we did is whenever there's a spot interruption notice, it's a event on AWS, so you can do whatever you want. It triggers a deregister Lambda. Deregister Lambda is nothing but what it does is it identifies which node is getting interrupted and goes on that node, figures out what all tasks are running on that node and what is the corresponding service and what is the corresponding ALB for that service. And it waits for 90 seconds for ECS to do the clean, removing and deregistering and everything. But for example, in this scenario, task C was dead in 2 minutes, but after 90 seconds, task A and task B were still running. So it will figure out all those things and make a deregistration call to the ALBs and deregister this instance from all the ALBs. So what happens here is, after 90 seconds, all the tasks will not get any traffic, and as a result, the users will not get any 502 errors. So a catch here is we take a hit on sort of availability. I mean, our systems can be loaded, but the fact that these instances would have been killed in another 30 seconds, and it's better to take a little bit more load than serving 502s. So that's a rational, that's a risk that we have took, that it's fine to send traffic to other healthy nodes. And another thing is, while we kill this, the new replacement tasks are already in the process of coming up. So maybe not in 30 seconds, they might come up in 50 seconds, but they will be up and take the traffic. There's one thing I want to talk about. I talked about in the eligibility criteria that we look for any service that can shut down in 2 minutes. But we missed the part that if a service is not starting in 2 minutes, it will still get killed and impact, and that's the reason we had to come up with this whole business. But the problem was, when you talk about stop time, you can configure that. But when you talk about startup time, there are a lot of variables that come into picture. So your app can start potentially in 2 seconds or 10 seconds, but then when you talk about a container getting started, you need to ensure that the new underlying infrastructure is ready. So if the underlying host is not ready, if the networking for that is taking more time, it all adds up to task startup time. So that being said, there's no easy way to add this part in eligibility criteria that the service should start in 2 minutes or 30 seconds or whatsoever, because there are too many factors in play when it comes to task startup time. So this is the Lambda we came up with and handle this scenario. There are some other scenarios as well, which we are working right now on figuring out how we can manage them or handle them. So one being, there are times when we see a lot of high interruption rate within a short span of time. So for example, 30% of our capacity goes out within 10 minutes. So this is one thing that we observe or monitor. Right now, we don't have automation around it. We are still trying to figure out what's the right thresholds when we should kick in the automation. So if this happens, that 30% or 40% of our capacity goes off within, say, 30 minutes. Right now, we page someone, and that someone comes online and looks if this is something where they should roll back or not. But this is a future plan where we will come up with some sort of automation once we figure out what should be the right threshold for this. Another thing that we have observed is at times what happens is whenever there is an interruption, ASG is unable to spin up the replacement instances. So what happens is, let's say 30 instances are killed. ASG will spin up new 30 instances, but there are times when it fails to do so for 20 minutes or something like this. So right now we are paging for it, but we are trying to figure out what's the right threshold where we can say, if ASG is unable to get the replacement instances for 20 minutes, just roll back from Spot. So we are trying to figure out what's the right threshold. Also, sometimes it's just one-off instance and where ASG is unable to replace, but then it's fine. So these are the two things which is sort of manual and not manual, where the decision making is manual, but rolling back and everything is automated. Coming to what we see after running all the Spot, again this is a AI generated image. So after running Spot, what we have started seeing is a lot of our peaks are now run by Spot instances, and on-demand usage is going down. And this is after a conservative rollout. We are not yet at a point where we are running 50% Spot, so we want to ensure that our rollouts are gradual and there is no hit on the availability of the system. So that's why we are doing gradual rollouts. And with this is where we see that we are not underutilizing our savings plan as well, and we are not spending too much on demand. So with this, we have achieved meaningful savings without impacting our availability of the system or reliability of the systems. And given we have this automation in place, it helps us to do safe and gradual rollouts. We don't have to, say run everything on Spot. We can do 5% Spot, 10% Spot, 30% Spot, and so on. And we know it's safe because any service that runs on Spot goes through that eligibility criteria. And the biggest advantage we have got is that whatever fine-tuning we are doing, it's on the workload level and not on the infra level. This is our biggest advantage. So with all this automation in place, even though this right now seems like very ECS specific, but these principles can be very easily applied on any platform, say Kubernetes. So in ECS world, we are updating capacity provider configuration, but say tomorrow we want to move to Kubernetes, all we gotta do is just extend our tool, do all the decision making, and instead of updating capacity provider configuration, we can just update the node affinity part of Kubernetes deployment and then carpet and take care of it. So in ECS world, there isn't a lot of options to use from open space world or anything. It's very cloud provider type, but Kubernetes world has a lot of tools available. But when we were looking at it, there's nothing that can do the decision making part for it. So for example, when people use Kubernetes, Carpenter is one of the tools that everyone uses. It can run your workload, it can decide when to run on demand and when to run on Spot based on different parameters, memory, CPU, or architecture, but it cannot take workload aware decisions that is this workload eligible to run on Spot or not. So this is what our engine does. It takes the decision and then it tells the orchestrator that you run it on Spot or not. So irrespective of the platform, tomorrow we can do the same thing on Kubernetes, do the decision making, and let Carpenter take care of rolling out stuff and running the underlying hardware. So that's my time, guys. Thank you. Open for questions. Sure. So yes, the question is how do we ensure that some of the replicas are running not on spot? So in ECS world, for any service, you define the capacity provider configuration. What it essentially is, are you comfortable with Kubernetes? Huh. So okay, in Kubernetes world, think of it like node affinity configuration, where we say two node groups and give weights. So for example, we say 40% on spot. So in Carpenter, well, you give node pool, and there we give weighted things. So similarly in ECS, you have cap provider configuration where you can say which capacity provider it should use. So for any service, we say run 40% on spot and 60% on demand. So that being said, in our criteria is we never want to go more than 50% for spot. So at any given point, if a service is running two workloads, one of the workload will be on demand. Yup. So every workload runs on two node groups. One is on demand and one is spot. We just change the percentages. So it could be 0% spot and 100% on demand, or it could be 50% spot, 50% on demand. Any more questions? Yeah. Yep. So that's a percentage. What we did, we started doing a gradual rollout. So we first started with 5% spot, because there is no one rule that works for everyone in spot. You have to run, see what works, and accordingly adapt. We started off with 5% spot and see that okay, everything is working fine, there's no problem, and if there are any problems, we catch on early. So for example, the problem I said about 502s. So if we were doing 50% spot, it will be a massive problem. But given it was just 5%, we got it early, worked on it, fixed it, and then gradually rolled it out to 10%, 20%, 30%. So we do gradual rollouts and see how spot is, how our services are responding to it. Are there any issues or are there any errors? So accordingly, we decide, and we have come up with a criteria that we will never go above 50, given if we do that, there's a risk that if spot goes off 100%, which is rare but does happen, we don't want to be in a problem like that, that we don't have underlying compute to run our workloads. So to answer your question, it's us who decide that percentage. It's a human thinking that 5, 10. Exactly. So for example, during Black Friday sale, so Black Friday is this time where you don't have any spot availability. So we saw that okay, spot is doing really bad. We are seeing high interruptions. So first we tried reducing the spot percentage, and then during Black Friday, we completely rolled back spot. We set it to 0. And once the Black Friday was gone, we saw that okay, our SPS score is looking good. We started rolling it out again, but instead of going directly to 50 or 45, we realized okay, 30 is a very good starting point for us. Instead of 5%, now we started at 30, and every week we just added 5, 10% and aim to reach 45% or 50%. Wherever we see that okay, everything is healthy and our systems are reliable and there's no hit on availability of the system. Yeah. Sorry, can you? When you say data service, you mean any service which has state involved? No. So uh, while doing the technical design of this was very clear to us that we do not want to run anything which is stateful, because if the instance is gone, the state is also gone. So that's the reason we consciously make the decision that we do not want to run any stateful application on spot instances. Same goes with Kafka, because if the Kafka worker is moved to a different node or shut down, it has to do all the rebalancing and all that, which is expensive. So during the design phase, while coming up with the criteria, we came up with the criteria that okay, these are the limitations, and that's the reason we don't want to run these services on spot. So before working on any of this, we spent some time doing our research and coming up with a technical design and how it should be implemented. So during that phase, we figured out okay, this is not the right thing. Cool. Any other questions? multi-region. So when you say about multi-region, the way we handle multi-region is very different. So it might not be relevant to this. So we don't really run service in a way that
stack, most of our platform applications are written in Clojure. Our platform is almost 10 years old. We started like 10 years prior, and so we kept embracing Clojure since then. But the newer applications we have written in Node.js, Python, ROR, Postgres, Elasticsearch, Redis, ClickHouse, and so when it comes to publishing news, uh, the offerings we have is basically everything that is required by a digital newsroom, which covers the CMS, the headless CMS which we have, a page builder or what we call a website builder, then mobile apps. For engagement, we have applications for monetization, for analytics, everything which is required for digital newsrooms. And the challenges which we try to solve every day. One is, yes, real-time content distribution. Any news that is published needs to be published real-time on all the devices, like on web and mobile. And taking care of the spikes, the traffic spikes is something we just do, like it is bare minimum that is expected out of the products. And SEO is very important, like the content which is created, its distribution and discovery. So core web vitals, Google's core web vitals are very much like we always have an eye on the scores, and then constant challenge of managing infrastructure at scale along with the costs, and while maintaining the agility of like as we have a SaaS and PaaS platforms, we don't want to be the bottleneck when it comes to deployment. So we take care of speed and flexibility while maintaining the infrastructure. We try to solve these challenges. We think we are doing fine at these things. So would be happy to share and discuss insights on any of these topics. That's all. Don't want to take a lot of time. Thank you, and we are happy to host today. Thank you.
Like this. Okay, this is good. Yeah. Okay, hi, I'm Shubham. I am from True Foundry. I have been working in this field of cloud native engineering for the last 6 years. In total, I worked for more than 9 years now. Yeah. Yeah, so that's basically about me. Before True Foundry, I was working in Gojek for around 2 years. Right now, so True Foundry is a ML platform. Right now, we also build AI gateways, but that's a different thing. So KubeElasti is basically a tool that we have built. It's louder. KubeElasti is an open source tool that we have released for the community. It has been selected within CNCF Sandbox recently. I'll go through what that tool is, what that tool does, and the overall agenda. So the agenda is basically what the problem was, what we were trying to solve, how we arrived at the problem statement of scale to zero, how we decided to solve it, what other options are available, and then we'll go through a demo. Okay, so the problem is actually very simple. This is typically the usage of a typical cluster, a Kubernetes cluster that we encounter. So it might not be visible. The usage is around 2.6 and the allocatable is around 167. So this is less than 1.5% of utilization of what you're actually paying for. So this is a massive problem in the industry. Like maximum people hit like 10 to 15% in many cases of actual CPU utilization. You can see some spikes over there, but those are very few. So this is the problem that we were trying to tackle. So there are two halves to this problem. One is how do you actually right size the workload? How do you actually right size the pods that you're running? And second is how many pods are you running? So we decided to tackle the second question first, which is basically can we actually switch off services which are actually not receiving any traffic at all? So that's scale to zero. Scale to zero is similar to any serverless platform that you might have heard of. And we wanted to implement that in any Kubernetes cluster without using a lot of external dependencies. So these were our requirements. We want to scale to zero on zero traffic. We want to resume service if traffic has come back. We are not okay to accept any dropped traffic. We want to use native Kubernetes resources only, and we don't want any additional latency. We also wanted it so that we don't have to rely on a particular cloud provider or an ingress provider. So So for example, by ingress provider, what I mean is Nginx, Istio, Kong, anything, all of that should work. Right. So it started with a search. So these are the few options that we found in open source. So that is Knative, KDA, HTTP add-on, and OpenFaaS. In case of Knative and OpenFaaS, the problem was the barrier to adoption was really, really high. Because in case of Knative, you have to actually migrate yourself completely to a different, their own CRD, their own Knative service. In case of OpenFaaS, you have to model everything as a function. And in case of, and there's a project under KDA. KDA is event-driven auto-scaling in Kubernetes' context. They have a project called HTTP add-on, but the problem with that project is that it adds a proxy which remains in the hot path, which remains in the request path for the complete time. So it adds external latency, additional latency, and some reliability hit. So yeah, so basically we set about building KubeElasti. And so these are the things that KubeElasti does. It scales down to 0 when idle, scales to 1 on traffic. It uses a smart proxy that steps out after scale up. It integrates with HPA or KDA. So if you're already using HPA or KDA, you can basically, it hands over the part of 1 to N scaling to these other tools. It works with an existing plain deployment plus service setup. It does not need any kind of change to most of the Kubernetes setups out there. It has no barrier to adoption, and it is open source. Right. So how it works? So how it works is actually very simple. If you don't have KubeElasti, you have a service which is forwarding traffic to pods. Traffic comes in, request fails because the pod is not there. If you have actually scaled down to 0. So how it is solved in some of the cases is you have the traffic to service is actually metered. It's actually like you get those metrics and you scale it up, but still like the initial few requests are going to fail. In case of Elasti, what we do is Elasti proxy basically injects itself in this path, and any traffic coming to the service actually goes to Elasti proxy, and it queues those requests. It queues those requests, and on the side it brings up pods for that deployment. So once the pods have come up, it will basically forward that request so that that request ends up getting served. So you get 0 downtime as a result of this. How this is actually built is it has 2 components, a resolver and a controller. I hope that is visible. Within the yellow box, there is a resolver and a controller. So resolver is basically the proxy that holds the requests in memory, and controller is the one that takes care of actually scaling the replicas as needed. Not going into architecture too much, but broadly, there are 2 modes to it. There is the serve mode and proxy mode. Serve mode is what you see right here. A request comes in, hits the service. We are in serve mode, it goes to pods. Our Elasti is running out there. It is talking to Prometheus, basically trying to figure out should I scale this service down to 0 or not. It decides that this service can be scaled down to 0 since there is 0 traffic. It scales it down to 0, and what happens is Elasti resolver actually injects itself in the path of that service so that all any further traffic, if it comes in, it actually hits the resolver. Right. So when traffic actually comes in, Elasti resolver gets it, it queues it, it informs Elasti controller that the pods need to be brought up. It brings up that pod, and then resolver forwards that traffic to the pod, and then it takes itself out of the path. So any future request actually goes directly from service to the pod without having resolver in between. So there's no additional latency or reliability concern beyond the initial few requests. Right. So this is one of the use cases that we have found to be where this was extremely useful. So this is a dev environment. In dev environment, basically what we had is, we have 2 services, 3 services in fact. We have a front-end service and 2 back-end services. For front-end services, we wanted a PR preview to be available for every PR that is raised on that repo. So we have 3 different PRs raised. In normal condition, what would happen is if you want a PR preview to be available for every PR, this is something that you would have used external tools for within your own companies, but this is something that we built in-house. So you have 3 different PR previews available to it, and all those PR previews have to be up for this to work. So without KubeElasti, there's no traffic in the system, no PRs are undergoing review, and we still have 5 services being up. The traffic is flowing through front-end PR1, but still, like, we are continuing with 5 services. So the obvious saving over here is none of this has to be up if there is no traffic flowing in the system. If traffic does flow through the system, that is the one that needs to get activated. The other front-end peer services can remain at 0 replicas. So if you just calculate through this cost, what it basically comes down to is, let's say 20 open PRs, 2 PRs actively under review, and each PR taking 0.5 vCPU and 1 GI memory. So that comes to around $315 per month per service. Right. So coming to how it is actually used. So this is a typical Elasti service that you would use to get Elasti to intercept your requests. So this is an Elasti service. You can see 3 parts to this. That is actually an input. So there's the service, which is target service. So this is the service that you want to intercept. Then there's the scale target ref, which is a target deployment. So this is the part that you actually want to scale. This is similar to how HPA is designed. And then there is triggers. So in triggers, basically what we have is what is the query that Elasti needs to make in order to figure out whether it needs to scale down or scale up the requests. Right. So this is a small demo, 2 minutes. So I'll go through this. The guy demoing over here is Raman. He has written most of the code in this. So yeah. Okay, this might not be. Is this audible? So limitations wise, you can like basically the limitations are similar to any serverless platform. Anything with high cold start time, like GPU workloads, they do suffer from a large time for provisioning because of cloud provider delays. So that is one case where this will not work. Any setup where the traffic does not go through a Kubernetes service, because we intercept Kubernetes services directly. There are some cases where load balancers are performing health check on services. So that is something which we are in the process of figuring out. And anywhere where the infrastructure itself is not flexible. So if you have an on-prem Kubernetes cluster where nodes are not provisioned dynamically like in Carpenter, that is where you will face some problem with any serverless platform. Like basically you won't realize any cost gains over there. Yeah, so that's basically about KubeElasti. This QR code will take you to the website for KubeElasti. We are actively looking for contributors, maintainers, anyone who could get connected. So yeah, please feel free to jump in. Any questions? Yeah. Yes. Right. Yes. So the question is like, can this actually be run on production? Because this looks like something that would be good for dev because there is low traffic, right? Yes. on a low traffic, low reliability requirement service. But in case of prod, basically, if you have a service which has low traffic, or even if it's similar to what the previous, like what we talked about in Spot, if the time for a service to come up is really small, then it's actually fine. If that service is going down to zero traffic, then it's fine. You can run that service behind KubeElasti. It will come up in, let's say, 30 seconds. That's fine if you can tolerate that. Yeah. Right. That is true. We have not encountered such a situation. That can obviously happen. But yeah, the way to solve it would be to vertically scale the resolver. That is a horizontally scalable, completely stateless system. Like you can solve it using scaling. Right? Order of requests coming in would not be preserved, I think, yeah. Because all of that is in separate Go routines, which have their own setup. Yeah. I mean, this basically makes the resolver like stateful to some extent. So yeah, that could be a good idea. We could write to disk and then basically load it up from there. Like we could make it stateless, but then like we lose the HPA, like basically being able to horizontally scale it to infinite. So yeah, there's a trade-off there. Yeah, you had a question. Yes. Right. Yeah. Yeah, in that case, basically, like if the request, like the token that is coming with the request, if it is that close to the expiration window, then there's always a chance that it goes over. Yes. By the way, the question was, what if the request had any authentication information, which might end up getting expired by the time the pod actually comes up. Right. 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 So 0 to 1 is something that so 0 is by definition low traffic. So if 0 to 1 is what KubeElasti handles. Everything after 1 to n is handled by other autoscalers. So you can use HPA, you can use SCADA. So yeah, right. So Elasti service can be configured in that way. So if I can show that. Uh, yes. So this min target replicas, you could start with a large number of replicas, if that would help. Yeah. Yes. Like the middle ground. So the question is, why go to 0? Is there no middle ground? So the middle ground is basically making your request smaller, right? So that is something that VPA does in case of Kubernetes. But at the end of the day, like this is a problem that we faced because a lot of people had a lot of services running just in case it receives some kind of traffic. So that is the case that we started it with. But what you said, you can save a lot by actually sizing it very low, sizing a particular pod. But even in that case, a single pod can take up a lot of resources. So yeah, like 0 is better than 1 always. Yeah. The vertical auto scaling part. That's a separate project. We have some plans around that. Okay, if that's it. Thank you. He has a question. Yeah. Right. Right. So the question is, why not make it sort of like a window? Like in a certain kind of in certain window, I want more resources. In a certain window, I want less resources. Is that right? Yeah. You could do that, but then like again, you could do that, but zero. Zero is less than anything like that. Like if you can get to zero, you better get to zero. Otherwise, yeah, obviously, like you can do some other things around it. Another point there is, if you actually like memory is not something that can easily be reduced a lot. Even a single replica, even with very low traffic, you're not going to use up a lot less memory. CPU, it is true for CPU, but not for memory. So you will end up paying for memory in most cases. Yeah. So how much time does it take to go from 0 to 1? So it depends on the actual pod. We wait for the readiness probe of the pod to pass. If the readiness probe has passed, we forward traffic. It can be as quick as 1 second, like like less than 1 second. But it depends on how long does it take for the node to come up. How, like if you have flexible infrastructure, and how long does it take for the pod to actually get scheduled and start running and be ready. So that's why I mentioned one of the limitations, GPU with GPU workloads, it does take more time because the node provisioning actually takes more time. But if you can tolerate that initial latency spike, then you can save a lot by just scaling GPU workloads down to zero. Yeah. Sure. Right. Right. I mean, so for Deliveroo, that might be true. You guys get a lot of traffic, but yeah, for for low traffic scenario services with low traffic, you can use it. If the number of services is large, you will get more savings. Thank you.
Is it better now? It's better. Okay. Cool. Just give me a minute. Thank you for joining me today in the talk about scaling microservices with Halyard at Confluent. Yeah, before I get started, sorry, you were telling something? Okay, yeah. Yeah, I'll introduce myself here. Sorry, louder? Okay, sure. I'm Mustajab. I'm a senior software developer here at Confluent, and today I'll be talking about scaling microservices with Halyard at Confluent. And before we get started, I would like to know how many of you here have heard about Confluent. Can I get a raise of hands? Okay, that's a few people. How many of you have heard about uh, Apache Kafka? Okay, that is a few more. How many of you have heard about Apache Flink? Okay, that is a little less number. Okay, for those of you who don't know about Confluent, it's a data streaming platform that empowers organizations to make real-time decisions by using data streams, right? And Confluent provides Apache Flink and Apache Kafka-based solutions which help help companies take AI-driven decision with real-time data. I mean, AI requires real-time data for it to take the best decision, right? So Confluent comes in handy there, and we also have event-driven architectures which happen because of this, and we have shift-left data which comes into picture because which basically means that you move to the closer to the source and process the data there as much as possible so that the downstream systems end up having the data in the right format and they work as expected. Yeah, and many other things that Confluent helps you go through. We discussed about the products that Confluent has to offer: Apache Flink, Apache Kafka, and there are many more like TableFlow, and then a few more that it does, Connect and things like that. So in order to make all of these happen, Confluent has like two offerings that it has. One is the cloud-based offering, and one is the on-premise based offering. For the purpose of this talk, we will be limiting it to the cloud-based offering that Confluent has to offer, and the deployments that go through in the cloud-based offering. Yeah, and we are deployed across all the public clouds that are there. So we have like 90+ regions where we are deployed, and this basically helps us meet the customer where they are and fit their needs when required. There is another distinction in the deployments that we have. We have services which get deployed in the control plane, and we also have services which get deployed in the data plane. Now, most of the services that get deployed in the control plane are Helm-based services, like most of them. But in data plane, we also have Helm as well as non-Helm-based services, and this deployment platform that we're going to talk about today takes care of both of them, and we'll look into it how. Now, we discussed about the landscape, but what is the scale that we handle at, right? So to talk about the scale, Confluent has like 1,400 microservices running. Trust me, these are needed, but not that we've made up these services or just doing it like that. Yeah, and we have around 5,000 clusters which are present, and all these services are running on a bunch of these clusters. And given we have more than 5,000 service clusters, and we have these many microservices present, you might expect that the peak load that we see is a multiple of these two, like that's the combination, right? But that's not actually what we see. The peak load that we see is around 10 power 5 per day, because not all services that get deployed, they're not deployed to all clusters. They might be limited to just the control plane or just the data plane, and even in data plane they might just be limited to a certain set, like maybe Azure clusters or maybe GCP clusters or things like that, right? And before we get into the crux of the platform that I'll be discussing, I also wanted to talk about what are we trying to achieve. So basically continuous deployment, right? And what does it mean? I mean, most of you might know about it, but just to jog your memory, it is a practice where automatically validated code change gets directly sent to the customer without the involvement of developers a lot. I mean, it's a dream scenario, right? Well, customers, where developer just clicks a button and then the code change gets validated. It makes sure that nothing is breaking, and then after that it gets promoted to the next environment and things like that. And ultimately the customer receives the code, and the feature which had to be released gets released as easily as possible. Now, introducing our unified deployment platform, or Halyard, which we used to call it previously, which solved the deployment problem at Halyard, at Confluent. Unified deployment platform is a fully integrated, cloud agnostic, continuous deployment platform. Like I mentioned, it was present across, we need to be present across environments and need to make sure that everything, all the customer workloads are working as expected. And we need to manage both Helm as well as non-Helm based internal microservices in Confluent Cloud. Yeah, and there are a few. These are some of the features that we have in this platform. I'll be going through a few of them as a part of this talk, and in future. Yeah. So we have a bunch of technologies which we use to make this happen, and these are a few that I've listed here. Now, the crux of any deployment platform is the version that gets created, right? The version, or the version, basically what gets deployed and where it gets deployed. So that is what we'll be talking about in this. So the version is in Confluent is basically a YAML spec that the developers define in their own repository. So we have like 1,000 services. So we have 1,000 YAML files which are present in their own repositories across GitHub, and the complete ownership of that is present with the service owner. Now, for example, here we have service as the ultimate object which has the metadata about the service, and it also has information about about who can deploy and many other RBAC details like that. And you have multiple cluster groupings present within a service. So this cluster grouping is basically a target of clusters that is defined for this particular service. So for a particular service, you can have like development cluster groups which are present, and you can have like prod cluster group which is present. And the configuration for each of them is, the target is defined in this YAML file again. We'll discuss about how the cluster grouping happens and in the future, in the next slide. The next object in this is the version, right? So the version is basically a snapshot of all the configurations which the service will use in order to come up and connect to whatever the relevant microservices or whatever it needs to do. Now, how does this change in GitHub? I mentioned that this was present in GitHub, right? How does this change in GitHub come to our system, the unified deployment platform? And that happens with a merge to master. When there's a merge to master in the GitHub, which happens, the YAML spec, if there's an update to the service level details that we have, we would update that in our UDP, in our platform. And this, in a similar fashion, if there's any update to the cluster group, it would again contain, the cluster would be either updated or created, or depending on what happens, it would be like, it would be updated. And we also have the version which gets created. The version is basically like a number or a tag which is given to the service owner, which they can use to deploy that particular configuration on their clusters, whichever they intend to. And within a service, I have mentioned this before, but within a service, there are multiple cluster groups, and each cluster group will have one version, like multiple versions associated over a period of time, right? But at one point of time, like it's a snapshot, the version. Now, coming to the cluster targeting, I mentioned that we have some services running on just a few clusters, while some of the services might be running across clusters, right? For example, if there is a telemetry service or maybe the logging service which is needed for collecting the logs and metrics, it should be present in all the clusters, right? You want to understand what is happening in all the clusters. So we want to provide the users the flexibility to define where they want their service to be installed in and with what configuration, if it's possible. And to do this, we have the cluster grouping that we discussed previously. The cluster group. So here, service A has two groups. Group A, service A will target just the cluster 1, but group B of service A would target cluster 3. It can so happen that all of these clusters are again targeted by just one group, but that's not the case here. And in service B, we can see that there are multiple again cluster groups present, and all these cluster groups can be defined by the owner, by the service owner itself. We don't mandate that this cluster 1 and cluster 2 are supposed to be present in just the group A or group B. We give that flexibility to the service owner. And how do we do this? Like to get into the details of this, we have a cluster which has some metadata present with it. So it has a bunch of regions, tiers, labels which are present, and these labels are then used by the targeting defined in the group to like target that specific cluster. So for example, in this case, it is a simple example that I've taken. Cluster contains label A. If the cluster contains label A, target that. That's where we end up deploying group versions related to group B on that cluster. But this can be way more complicated, right? It can be just that the cluster it can be like cluster contains label A but not label B. It can be a multitude of things which come in, and this label that we define, it can be very fine grained. It can be just the cluster ID which is unique to every cluster. So it can be like target cluster 2, or it can also be like a broad thing like target all the clusters in the prod environment, or target all the clusters in the stage environment, something like that. It can be way broad, or it can be like GCP cluster, all the GCP clusters. So it's all of that is a possibility and flexibility that we provide to the service owners. Now, we spoke about how the version gets created and how the targeting happens. We will be looking at how the version gets deployed, right? So in order for the version to get deployed, we have the service owner would need to trigger installation request on the CI or through the UI. We provide a bunch of options like this, where they specify which service, which version, which deployment, which cluster grouping that they want to deploy to, and they also need to specify in case they need, specify the clusters that it needs to be deployed to. After this comes the orchestration layer, which takes care of batching the eligible clusters, or maybe even selecting which are the eligible clusters. This is needed because in case the cluster mentioned by the user is not a valid cluster for that particular service, for that particular cluster group, then we need to make sure we need to cross-check that, right? So this basically does that. We can't be completely dependent on the user's input because we might end up installing wrong services where we don't intend it to. And after this batching is done, in the orchestration layer, we also provide a way to like do progressive rollouts. So this is very important in case you want to reduce the blast radius. So you want to first release the change to like 5% of the cluster, then the rest 5, and then so on, proceed like that, right? So the orchestration layer also helps you batch it. It gets the list of all the clusters, then it creates batches in the way that is needed, and then it issues a install command on all those clusters to our platform. And this install request which comes in, it involves like rendering the manifest and and getting the exact details of what need to be deployed. Like we have multiple templates which are present. Those need to be like resolved. Like we need to understand what are the cluster groups, and all of that happens in based on the cluster. There might be some metadata from the cluster used in the charts. Using the data again, we render the charts, and then once we have the chart rendered, we have something called as an operator present on all the clusters. So we had like 5,000 odd clusters. All of these have like an operator which is shown here. So the first object that you see on all of these clusters is the operator, and it's present on all the clusters. Now once the rendered manifest is generated and stored with the platform, the operator keeps continuously polling our platform. And given this platform it acts like a core service, and then there are multiple agents which are present on all the clusters that we have. Now with this polling which happens, as soon as there's a change to the rendered manifest, what ends up happening is the operator picks this change up and then starts applying it. We currently use Kubernetes manifest apply, and then we are moving slowly towards Helm-based application, and the operator applies it. Now you might also notice that there's an other operator for non-Helm-based things, right? So this is basically required for non-Helm. This operator is deployed by the base operator that we have, and that takes care of all the scaling up, pod that needs to be present, managing stateful states, all of that in the non-Helm based products that we have in place. Now, yeah, this is about the install, and coming to the next part, yeah. There might be some cases where you don't want any deployment to go through, right? Like we recently had Christmas holidays, and that tends to be a lean period where people don't want to deploy anything, or many people are on leaves, like they don't want to work. And in that case, you don't want someone deploying a change where it breaks something, and then everybody has to come and work and figure out what is happening. And in order to solve for this, we have something called as maintenance block, which is applied. And this is again very configurable to to have a certain number of clusters, or it can have a certain number of services. And once the service or the cluster matches, the installations wouldn't happen. It's basically blocked from happening. And yeah, that's about the version deployment flow. Now, I spoke about continuous deployment, and I mentioned to you that it's very important that continuous deployment happens where there is real-time monitoring which is taking place, and it happens in phases basically, right? From one environment to another, and in between there is bake time, and then there is monitoring which happens on all the required metrics, making sure that everything is fine. Now, in case of progressive rollout, we have this case that we support both sequential rollouts, which is basically given a phase, like the customer is free to define, the service owner is free to define whatever cluster set as the first phase that they want to. So they can have first set of clusters defined. In this case, it's based on region. So there are multiple regions which the service is getting deployed on, and that is happening in waves. Now, with serial, we allow, it's pretty self-explanatory. We allow the deployment happens one after the other, and after each wave is complete, we have some bake time, and then we have post-deployment and pre-deployment checks which run in order to make sure everything is fine. And if something has gone wrong, then we roll back the change, or we make it stop there. Like depending on how the customer, the service owner has configured it. It can easily be that they just want to roll back, or the other way around. And in this case, it was successful, so it proceeded to the next wave, and sequentially this happens. Now this is a very simple thing that I've shown. The service owners are free to create more customized and more complex workflows if they need to. Now, coming to the parallel workflow that the progressive workload allows, I mean, within a wave, you can have like all the regions targeted just at once. And again, you'll have bake time after everything is successful, and then deployment, making sure that everything is fine. Now, this another requirement that we had, where we had like 3-4 services which need to go in together. Like Kafka goes in, then there's a RBAC change along with that which needs to go in, and then there is another different service which is also need, like something like networking, for the Kafka change to work as expected. In those cases, again, we support that functionality where users are able to specify multiple services that need to happen, and it can either be sequential, parallel, however they intend it to. And the deployment checks or deployment checks that would happen, it would happen either based on the configuration of the user, where we basically go look at the monitors that they would have given us. So these monitors are basically metrics, based on metrics, where where the services emit metrics, right? So we use that and have defined some monitors, and those monitors get used to understand what the state of the service is, and then proceed. Now, in all of the cases that I discussed till now, the deployment, the installation had happened through a user triggering it. Like user had, the service owner had triggered it. This would go through a CI or maybe a UI, and then it would trigger the unified deployment platform, and then that would trigger an installation, right? But then there is also a case case of cluster bootstrapping, where the Confluent customer takes an action due to which it triggers a cluster creation. Now in this case, we encounter a chicken and egg problem. I'll talk about that. So basically, once the customer has triggered a cluster creation due to some reason, it can either be that they've asked for a dedicated cluster, or the multi-tenant cluster has run out of its capacity, and then we need to use a new cluster or something like that. In such cases, we have a provisioner service. This is a thing different from the deployment platform, but this basically sets up the infrastructure of the cluster that is needed. It makes sure that all the basic infra which is needed, like networking and pods that need to come up, autoscaler, and all of that are present on the cluster, and those things, nodes that need to be assigned, all of that is taken care by the provisioner service. Now, but the problem is, we don't have the operator which does the deployment of the services on this cluster. Now, if this is a Kafka cluster, we want Kafka related services to be deployed on it, but we don't have the operator here. Now, who deploys the operator? So, like, it's a chicken and egg problem that we end up at. And here, the provisioner solves this by going to the deployment platform, understanding what, getting the operator manifest, and then manually applying it on the cluster, and then creating the operator for us. Now, once this operator is up, it goes and fetches all the default versions that need to be installed on the cluster. Now, these default versions, if they were present in a GitHub file, we wouldn't be able to do it. And this is why we have had to move away from the GitOps model in our deployment, because the default version that is present, it needs to be present in our DB, and our deployment platform needs to be aware of what the default version is at a given point in time. And this is why we store the default version and version information in our DB, and then after the operator fetches all the default version, it gets stored in it then brings up all the services that are needed, and a bunch of services that are needed on the cluster would come up, and that's how this whole flow would complete. Now coming to the current and future developments that we have here. I mentioned that we are currently using the a custom CRD that is the operator that is there, which is a custom controller which is there, which I've written, and this applies all the manifests on the clusters and make sure that all the resources or whatever is needed comes up. Now we are moving to a open source controller there, which is FluxCD, which would support more Helm native features and things like that. And we are also looking at possibility of getting rid of the operator altogether. That's the agent that I'll be talking about here, and manage the deployments completely centrally. This has some scale issues, but yeah, we are exploring how we can fix that and get around it. And we are also looking, we have CLI tooling which is present, so that users can interact with our platform, understand what is deployed, what are the targeted clusters, what are the service details that are currently present in the DB. The interaction of all of that is taken care by our CLI, and that CLI we are looking at integrating it with our LLM tools that we have in-house to help make investigations faster. Cool. I ranted about this for about half an hour, but you might be wondering, why do we need this? Can't we use an open source solution or a third party solution that we have in place? And why do I have a job around this? And why does my team work on this? But the crux of the thing was, when we did the evaluation, there were not a lot of products which were cloud native and finished and had all the features that we requested, and it did not either have the integration with the Confluent ecosystem which was present. Like, we had a bunch of Confluent specific lifecycle tools which the integration was needed, and for that we had to build our own system, and there were a bunch of other security requirements which was to be taken care as well, like the RBAC that I mentioned. Like, we had to control who could deploy a particular service, and that had to be present with the service owner. They had to take the decision on who could control the deployments and things like that. All of that was not possible at that point of time. So yeah, we had built this, and we are actively, like I mentioned, that we are moving towards a FluxCD controller, right, which takes care of the deployment on the cluster. The operator is now moving to a FluxCD controller, and that things like that we are trying to integrate open source tools as and where possible, and maybe even third-party tools. So yeah, this evaluation was done 5 years back, and I think that's it. Thank you. If you have any questions, please. Sure. Flux controller or Argo Flux controller. We had done a comparative study on that. I don't remember the exact reasons. Maybe I'll get back to you around it. Yeah. So the question was, what is the reason why we picked Argo CD? Why we picked Flux CD controllers instead of Argo CD controllers? I think one reason that I remember was we had already used Flux controllers in one of the other projects that we were building, and we knew what to expect from that, and that we decided to use it here as well. So yeah. This decision predates me, but from what I understand, this was considered. Argo CD was considered as one of the options that we could have taken, but we like I mentioned, right, there were a few missing features like that were present, and integration with the other tools that were needed was not there at the bottom. Sorry. Okay, what is? Yeah. Yeah. Go ahead. Correct. So in the GitOps model, everything that we have would stay would reflect what is present in the Git, right? Git repository. But the problem with that was when there's an actual deployment, it makes sense. When the deployment is triggered by user, then it makes sense. But then when there's a new cluster which comes up, which was not previously targeted by any of these clusters, we still need to figure out where this cluster fits in, right? So that information we'll have to again either go back to GitHub and then fetch it from there and then do it. That we found it a little tedious, and we instead chose to do it in the DB where we have all the information present and then use that. Yeah. Sure. Correct. It would require, but we're still evaluating that. Yeah, I mean that's one of the possibilities that you mentioned. You can do it that way.